Let's build up Green's theorem from the ground up, starting with a picture, not a formula. Picture a rubber band laid down flat on a table, forming a loop that never crosses itself. That's a simple closed curve. Now picture walking along that rubber band. If the inside of the loop is always on your left-hand side as you walk, you're walking the positive direction, which is counterclockwise. So, a positively oriented curve is one where the enclosed region always sits to your left as you travel around it. Now let's name the pieces. The loop itself is called the boundary, and the flat region trapped inside it is called the enclosed region, which we call D. We write the boundary of D as curly D, D. Whenever you see that notation, it just means the closed curve surrounding region D. Here is the big idea. Instead of walking the entire loop and adding up a line integral, Green's theorem lets you swap that walk for an ordinary double integral over the region trapped inside. It converts a boundary walk problem into a flat area problem. Here is the formula itself. Loop integral over C of f dot dr equals double integral over d of open bracket curly dq by curly dx minus curly dp by curly dy close bracket dA, where f equals p, I hat, plus q, j hat. Take q, differentiate with respect to x. Take p, differentiate with respect to y. Subtract the second from the first, then integrate that difference across the whole region. Always q by x minus p by y, never the other way around. Let's use this on a real example. Worked example 1. Evaluate the loop integral over c of cosine of x I hat plus x squared y j hat dot dr, where c is the positively oriented boundary of a square with corners at the origin and at pi over 2, pi over 2. Picture a small square in the first quadrant, walked counterclockwise. Step 1. Identify the pieces. P equals cosine of x and q equals x squared y. Splitting this boundary into 4 separate straight line pieces would normally take 4 separate line integral calculations, but Green's theorem skips all of that. Step 2. Differentiate q with respect to x. Q equals x squared y, and since y is held constant, x squared becomes 2x, so curly dq by curly dx equals 2xy. Step 3. Differentiate p with respect to y. P equals cosine of x, which has no y in it at all, so curly dp by curly dy equals 0. Step 4. Subtract 2xy minus 0, leaves just 2xy as the integrand for our double integral. Step 5. Set up the double integral, using the square's own side lengths as the limits. That gives us integral from 0 to pi over 2, integral from 0 to pi over 2 of 2xy dx dy. Step 6. Integrate the inner integral with respect to x, treating y as a constant. Integral of 2xy dx equals x squared y. Step 7. Plug in the x limits. At x equals pi over 2, we get pi over 2 squared times y, which is pi squared over 4 times y. At x equals 0, we get 0, so the inner integral leaves us with pi squared over 4 times y. Step 8. Integrate the outer integral with respect to y. Integral of pi squared over 4 times y dy equals pi squared over 4 times y squared over 2, which simplifies to pi squared over 8 times y squared. Step 9. Plug in the y limits. At y equals pi over 2, we get pi squared over 8 times pi over 2 squared, which is pi squared over 8 times pi squared over 4 equals pi to the 4th over 32. At y equals 0, we get 0. Step 10. Subtract pi to the 4th over 32 minus 0 gives our final answer, pi to the 4th over 32. Now, worked example 2, a circle, and we'll find the same answer 3 completely different ways. Our vector field is f equals open bracket y minus log of sine squared of x close bracket I hat plus open bracket 2x plus the cube root of y squared plus 1 close bracket j hat, and c is the positively oriented circle of radius 2 centered at the origin. Step 1. Rather than trying to parameterize this messy field directly, apply Green's theorem immediately. Here p equals y minus log of sine squared of x, and q equals 2x plus the cube root of y squared plus 1. Step 2. Differentiate q with respect to x. The second term has no x in it, so it drops out, leaving curly dq by curly dx equals 2. Step 3. Differentiate p with respect to y. The log term has no y in it, so it drops out, leaving curly dp by curly dy equals 1. Step 4. Subtract. 2 minus 1 equals 1. Notice how most of the messy terms cancel completely, leaving something very simple. Step 5. Since the integrand is just 1, the double integral over d of 1 dA is a geometry shortcut. It simply computes the plane area of the region. Route A. Recognize the shape directly. The area of a circle with radius 2 is pi times 2 squared, which equals 4 pi. Route B. Set up in xy coordinates instead. That gives integral from x equals negative 2 to 2. Integral from y equals negative the square root of 4 minus x squared to the square root of 4 minus x squared of 1 dy dx. Integrating the inner piece with respect to y gives 2 times the square root of 4 minus x squared. The outer integral, integral from negative 2 to 2, of 2 times the square root of 4 minus x squared dx is exactly the area formula for a semicircle doubled, and it evaluates to 4 pi, matching route A. Route C. Switch to polar coordinates, usually the fastest choice for circular regions. We convert using double integral of f of xy dx dy equals double integral of f of r cosine theta, r sine theta, times r dr d theta, remembering that extra factor of r that always appears in polar coordinates. Setting this up, with r going from 0 to 2 and theta going all the way around from 0 to 2 pi, we get integral from theta equals 0 to 2 pi, integral from r equals 0 to 2 of 1 times r dr d theta. Integrating the inner integral with respect to r, integral of r dr equals r squared over 2. Plugging in the r limits at r equals 2 we get 2 squared over 2, which is 2, and at r equals 0 we get 0, leaving just 2. The outer integral becomes integral from 0 to 2 pi of 2 d theta, which integrates to 2 theta. Plugging in the theta limits, 2 times 2 pi minus 2 times 0 gives 4 pi. All three roots agree perfectly on the final answer, 4 pi, and notice the pattern. Whenever the enclosed region is a circle or part of a circle, switching to polar coordinates is almost always the fastest of these three routes. Now, what if the enclosed region isn't a simple circle or square, but some oddly shaped blob? Picture slicing the blob into two simpler pieces, D1 and D2, with an internal dividing line. Any complicated region can be split into simpler subregions, each handled separately, then added together. Here's the elegant part. Double integral over d of q sub x minus p sub y dA splits into double integral over d1 plus double integral over d2, which by Green's theorem equals loop integral over the boundary of d1 of f dot dr plus loop integral over the boundary of d2 of f dot dr. Picture walking around piece 1. You walk along that dividing line in one direction. Then picture walking around piece 2. You walk along that same dividing line, but in the opposite direction. Because line integrals depend on direction, the integral over the shared boundary in direction, 1 equals the negative of the integral over the shared boundary in direction 2, so these two contributions exactly cancel. What's left is only the true outer boundary, double integral over d of q sub x minus p sub y dA equals integral over c1 of f dot dr plus integral over c2 of f dot dr, where c1 and c2 together make up only the true outer edge of the blob. Whenever regions are combined, any shared internal boundary always cancels. Only the true outer boundary survives.